week's material. But this is where now we will see, it is on. This is where you will see the applications, and there'll be some more coming. Compared to the original proposal, this would be the last of the seminars in that list. I gave Dr. Raghavendra a list of some 7-8 seminars I could add. I could not estimate the time requirement very accurately. It was just some guesswork. So he chose the 3 seminars, including this one now. The other 2 you saw yesterday. But since we have time, I'll add some more seminars. And for the last day, I will add a general discussion on the title of the course. What is radiomics? What is informatics? What is CAD? And how do we, why do we do it? And how do we apply it in practice? And general discussion. So I'll add those files later to the same folder through Dr. Raghavendra. So today's application is detection of architectural distortion in mammograms, continuing the work that I showed in chapter 8 last week. I showed just the beginning part of that project, where we applied the method to segmented regions of interest containing architectural distortion and a few mammograms containing architectural distortion. Today you will see continuation of that work by 3 more students who got their MSc and PhD from me. So this project turned out to be a fairly big project, concluding our work on mammography and computer-aided diagnosis of breast cancer. And I'll list my collaborators and others later on. The project was in collaboration with the University of Calgary, where I worked, and my students and collaborators in engineering and medicine, radiology in particular, and screen test program, which was called screen test earlier in the 1980s until about 2010 or so. Then they changed the name. But essentially, it's the Alberta program for the early detection of breast cancer. As I mentioned, in a screening program, women in a certain age group are invited, voluntary, to come and get their mammograms taken. In Canada, it is from 40 years to 70. So women are asked to come every 2 years to get mammograms done, 2 per breast, the CC and MLO views. I'm not sure if digital breast tomosynthesis has been incorporated yet into the screening program in Canada, but in some parts of the US, that technique has also been included. And CAD systems have also been included in some screening program. Commercial CAD systems have been around for about 20 years, licensed by the United States FDA. And they are used, but they are used as what is called second opinion. The radiologist has to first interpret the mammograms, record the interpretation, and then look at the output of the CAD system, and then may or may not change the initial diagnosis. It is like if a radiologist has some difficulty or doubt about the current case, the radiologist goes and talks to another radiologist. The same thing, now it's a computer. So there have been many studies that have shown that a radiologist plus CAD is almost the same as a radiologist plus another radiologist. So you can cut some costs if you have a computer to assist a radiologist instead of the films being interpreted by 2 radiologists that was required before. Every case had to be interpreted by a minimum of 2 actual radiologists in a screening program. And then they replaced the second radiologist with a CAD system. And there have been many, many studies to show that this works reasonably well. Now you should note that radiologists are highly efficient if you consider the area under the ROC curve, receiver operating characteristics curve. It is not efficiency, it is a combined measure of how sensitivity varies with specificity. You must have seen ROC curves in communication theory or decision making, pattern classification also. So the area under the ROC curve of most experienced radiologists will be 0.92 or so out of 1. CAD systems may have just about the same, 92, 93. The radiologists and CAD systems may have similar area under the ROC curve between 0.92 and 94, but when you put them together, you go to 0.9596. And what is emphasized is that a CAD system need not duplicate what the radiologist does, or what a radiologist does. If a CAD system can catch what a radiologist may typically miss and help in catching such difficult to detect cases, then there is some benefit. If the CAD system does the same and shows here is this calcification, the radiologist, I can see that, I don't need your help. Here is a mass, well, I already saw that. So there has to be some complementary operating processes that will fill the gap and boost the total efficiency. That is where screening comes in. The screening programs are geared for that, to catch cancer as early as possible. So mammography. Mammography was introduced perhaps in the 70s and 80s. When I went to Canada, to Winnipeg in 1981, mammography was still fairly new. It was there, films were there and images were being taken, but screening mammography started in the early 80s to late 80s. And then this was promoted as a method to catch breast cancer early, but in the systems for mammography in the early stages in the 1980s, the radiation dose was substantial, films were not of good quality, digital detectors came only 20 years later. So women were concerned about the radiation, the effect of radiation, the bad effects of radiation, you know that. It could cause cancer. It could cause other problems. The breast has to be compressed, it's painful. And why go there and experience this pain, and there is this potential danger of radiation. So women were hesitant to go to screening programs. And eventually it changed due to improved imaging techniques, reduced dose, improved efficiency. Previously, the recall rate was more than 1 in 10. 10% of the cases would be sent for additional tests. Because mammography images like this were blurry and fuzzy, and diagnosis was not always completely accurate. So when there is doubt, the person would be sent for additional tests, biopsy and so on. So again, women were afraid or concerned that I go there and then I have to go for additional tests, and then at the end you're told, well, everything is okay. So that kind of a false positive ratio in mammography itself made mammography a bit difficult to accept and for the screening programs to be successful. Now the same thing came later on. Mammography was accepted fine, and then CAD came. And in CAD also we have false positives. Every system will have some false positives. So again, the concern was, well, we have a program that's running and women have come in and programs are running well. They need a certain portion of the population to participate in the program in order for it to be effective for the general public. If nobody participates, then the field will not develop any further. So a certain portion of the population should come and get this done. It is screening. Most of them will be normal. Fewer than 10% will have some breast disease, and less than 1% will have breast cancer in a screening program. So for that 1% or 10% of the population, the rest of the population has to come and participate. But due to continued education and information being provided and improved quality, it has improved, certainly. And mammograms don't look like this anymore. This is an old film mammogram. So what are the signs of breast cancer that a radiologist looks for in a screening program? Masses, calcifications, bilateral asymmetry, and architectural distortion. Now we saw these three. We saw architectural distortion a little bit, and it's been shown that this could possibly be a sign of early stages of breast cancer, or the term early can be put in different senses. Early stages of breast cancer or signs of early breast cancer, but terminology varies. Typically, it is a sign before a mass is formed. When a mass is formed, there will be distortion. When calcifications are, there could be some distortion. But that's not what is being considered here. This is without a mass or tumor. And that could possibly lead to something else, or it could just stay just that way. So these are 4 important signs of breast cancer. There could be other manifestations, but these are the major signs. Masses are caused by breast cancer due to what is called the desmoplastic reaction in breast tissue. The density increases locally. The cancer is developing, it takes up more blood supply. A mass is observed as a bright, hyperdense object, hyper meaning more dense compared to the surroundings. And a mass could be very small, like 1 or 2 millimeters in diameter when it starts, and then it could be fairly big. Calcifications, or what are also called microcalcifications, could be very small. I showed some pictures earlier, but they were zoomed in. If you look at this image, it's very hard to see these calcifications. If you zoom, you can see these bright spots. So a radiologist typically works with some zooming function, or with old films, there would always be a big magnifying glass. And radiologists used to sit in dark rooms with a film viewing box that has, it's a light box on which all the films are mounted. But to catch these, the radiologist would have to scan with a magnifying glass. So perhaps most of you can't see that there without the zooming. And if there is a dense region like this, and if there are calcifications in there, it's even more difficult. Bilateral asymmetry, we saw a few cases. The differences in the overall appearance of one breast with reference to the other with the same view. Both of these are MLO, right and left. And this large density area is not here. Is there some way to overcome that noise? Should I put my microphone somewhere else? This is okay? Okay. Now, architectural distortion. So this seminar and this project, which we started in the year 2000 or so approximately, is about architectural distortion. So in our studies, as the field developed, and I attended a number of these conferences, methods were described to detect calcifications. There were thousands upon thousands of papers, and then masses. Masses are more difficult to detect. The easy things are done first. Calcifications, yeah, you can detect them. Masses, a little bit more difficult, but that's been done also. Asymmetry, not as many papers on asymmetry as calcifications and masses. Architectural distortion, even fewer papers on computer-aided detection or image processing for detection of architectural distortion. So eventually we came to that stage with some understanding as to what it is through presentations by radiologists, pathologists, and so on. They showed slides, they showed mammograms, and some articles were written by the medical specialists. So Dr. Desertel, our colleague from radiology and the screening program, came up with some definitions and patterns that we could understand and develop algorithms to detect those. Otherwise, the definition of architectural distortion is very strange. As I said earlier, it says the architecture of the normal breast is distorted. That doesn't help us. That is what the name says anyway. So it is the third most common mammographic sign of non-palpable breast cancer. That is, breast cancer that cannot be felt by hand, by palpation. The normal architecture of the breast is distorted. That doesn't help us. No definite mass visible. That doesn't help us too. Speculations radiating from a point. That's an important feature or aspect of architectural distortion. You see these lines going in other directions. There could also be focal retraction or distortion, and there could be some concavities at the breast border. But this speculated pattern is considered to be the most important sign. But spicules could exist around malignant tumors too. We saw that. So around the edges of breast tumors, there could be speculations. But here, there is no mass or tumor in the middle. It is radiating from a point. So our algorithm that Fabio Iris, who did his PhD with me, he developed this. First, we said we will extract the orientation field using Gabor filters. The orientation field is the gradient and angle of the strength of fibroglandular tissue versus angle at various angles. Filter and downsample, the original or initial orientation field could be noisy. Orientation field, texture, flow, they're all similar in idea, but how you extract is important. Texture flow, as we defined earlier, is obtained using just gradient operators. Gabor filters will detect oriented components, as we have seen, and I'll show more. Then analyze the orientation field using phase portraits. I mentioned that briefly, I'll show you again. Post-process the phase portrait maps and detect sites of architectural distortion. So in our discussions with the radiologists, we came to the understanding that the direction of the fibroglandular tissue in a local window is important. The magnitude is not so important. The brightness, density, they are not so important. They should be denser than the background. That is, they are white patterns, not black patterns. But that's what we detect using Gabor filters. After that, what is important is the orientation and how the orientation is distributed in a window. We saw Gabor filters. They are the Gaussian, 2D Gaussian with sigma x, sigma y as standard deviation or spread in the 2 dimensions and multiplied with a sinusoid, here cosine. The design parameters that Fabio came up with, we said we are detecting lines or curvilinear structures. These are fibroglandular tissues that may go in a certain direction for a small interval of space, extent of space, and then curve and change direction slowly. So there is a certain thickness of these patterns. How many millimeters? Elongation, how long does it go in a certain direction before the direction changes? Is it just straight forever? Most likely not. And for a certain distance, there will be a certain orientation, and then it changes. Orientation theta at every pixel. So the design parameters for the Gabor filters for this F, the modulating sinusoid frequency is 1 over tau to match the line thickness to the cosine. Sigma x is tau divided by the scale factor. Sigma L is L times sigma x. Sigma y, the spread in one dimension, is L times spread in the other direction. That makes it anisotropic or non-isotropic. So there is some orientation, elongation in a certain direction. If it is isotropic, there is no orientation. And then you rotate with angle theta, whichever angle you want and how many other angles you want. And we went 1 degree, minus 90 to plus 90, or 0 to 180, but we mapped it minus 90 to plus 90, about the horizontal. So there is a certain scale factor to the Gaussian. There is a certain frequency to the modulating function, and then there is rotation. Multi-scale, multi-orientation. If you want, you can change L also. And you create a bank of Gabor filters, how many ever you want, for various values of L, theta, and F, or tau. So how many scales do you want? How many values of L? Is it important to change it? Do the results depend on that? So you have to analyze and find out how many angles do you want, how many filters. Do you want 180? Do you want 90? Will 45 be enough? So those are questions of implementation. I showed this. I'm repeating some because I don't have all of you all the time. So, but I'll go through quickly those that have. Okay. Those of the topics I have already discussed, I'll mention briefly. So here is a Gabor function oriented horizontally. Its frequency response is here. Impulse response in XY. Frequency response in U, horizontal frequency, V, vertical frequency, DC in the middle. So it's a bandpass filter oriented in that at 90 degrees in the frequency space or 0 in the image space. If you increase L, it becomes longer, it's stretched, and this becomes thinner. The bandwidth is reduced. Same center frequency. If you make the thickness larger, the filter moves to a lower frequency band. So frequency shift can be achieved by tau. Rotation. If you rotate that, this rotates. It's the same thing. So these are the design parameters, and by changing L, varying L, tau, theta, you get a bank of these filters, how many ever you want, for multi-scale filtering, multi-orientation. So here's an example of some picture, and by using that Gabor filter, we get this output, detects lines approximately here. Fabio did a study and showed that when you have this, it's a band pass filter. It is not only at that angle, but a small band around that. So a few other details at slightly different orientation will also be caught or passed. So there is a certain bandwidth and angle also for a given filter. And if you use that, you get these horizontal pieces of those objects. There will be some noise. There are all these little pieces here and there. They're all caught. If you want to measure the area, threshold this, count the number of pixels, multiply by the pixel size, you get the area of oriented patterns. The leaves are not oriented. Or you may say the leaf is that way and this way, but it's big. It's sort of round. So you're not going to catch those here. We're catching only these stems, or whatever you want to call these branches. In the case of a mammogram, here is a part of an image with architectural distortion. You may see some spicules here from the middle. We apply a bank of 180 filters, 1 per degree, and with some tau and L. And these are the angles. The maximum response is maximum response over the entire bank of filters. For every pixel is saved in the magnitude response image, and the angle of that filter that gave the highest response is saved in another array, and the angles are shown here. You can see some spicules corresponding to these lines, but some of these lines are hard to see. There is some noise. So when you filter this, you will get a better display. So we analyze that with phase portraits. As I mentioned earlier, phase portraits are a form of representation of a velocity field. A particle is moving in the 2D space with the velocity vector v, x, y, with the x and y components, and a linear equation is given here, a, x, y plus b. A is a 2 by 2 matrix, b is 2 by 1, this is 2 by 1. So that's the equation. Now, given this field of angles, what are A and B, the 6 values of A and B, that can generate something that is close to this orientation field. Depending on the eigenvalues of this matrix A, you get node, saddle, or spiral patterns. This is assuming that you put a particle here and there is a field indicating the movement of the particle in various directions. But in images, we don't have anything moving. So these lines, these angles are taken to correspond to the Gabor angle output. Okay? Phase portraits are related to a velocity field, but we don't have velocity. We are only looking at the angle of these streamlines, as they're called. But a mammogram has so many pixels and so many different patterns, so you can't just take one orientation field of the whole image and stuff it into phase portrait analysis. So you take a small window. Even for that region of interest, we use a small window. I don't remember the size, 41 by 41 or something like that. So we have a bunch of these angles and find A and B. That will minimize the error between the field given and the field generated by A and B. and put that through some optimization, nonlinear least squares and simulated annealing were the methods used, and find A and B, and you get some parameters. So now you have a parametric representation with a model representing the data here. If it is 40 by 40, it's 1600 values represented by 6 values. And then we translate this and scan the image, and for every pixel we ask the question, what are these two matrices A and B? What are the eigenvalues of A? And depending on the eigenvalues, real eigenvalues of same sign, there are 2 values for the 2 by 2 matrix. It is a node. So at the fixed point given by minus A inverse B of that orientation field given by the model, it says there is something at that point. The window could be here, it could say the focal point, the fixed point is there. Or the window could be here and it could say the focal point is somewhere else, and then we throw it out. It has to be within a certain distance from where the window is in the image. And at that point, there is some convergence. And the window could be here, and it could say the A inverse B is here, and it is a node. So at that point, you increment. Saddle, if eigenvalues are real, of opposite sign. Spiral, if they are complex conjugate eigenvalues. That is spiral, this is saddle. We are not interested in saddle and spiral, but we are just showing that there is some scatter of votes and they can be thrown out. Spiral, there is something, but we are not interested. Architectural distortion doesn't look like spiral. So we focus on the node map, and clearly at this point there is an accumulation of votes. So that itself is sort of proof of the concept that it works. But it's not so easy. When you apply it to a whole mammogram, again the window is there, applied on this top of this field, and you run all over the image, and you create this node map. And this is the node map. This is the area in the MASC database where architectural distortion was identified by a radiologist or whosoever marked the database. The magnitude field, only oriented textures, the density information is thrown away. The DC gain of Gabor filters is 0. But we're not detecting edges, we are detecting oriented structures. And as expected, they should converge towards the nipple, these patterns. You see some overall convergence here. But there are many other places where there could be intersections of multiple lines or edges. So yeah, that's like a speculating pattern. It gave a large value there and something here. So when you have an algorithm, it doesn't look at the image like how we would do. We would discard many details. But the algorithm says, oh, there is a node there, there's a node there, so many other. But what we want is that, and that is where we have a large response. And you can see here that there is a clear speculating pattern in the directions of the Gabor filters, giving the maximum response. And here you see some of these lines intersecting. So the method works, but with false positives. We need additional methods to reject all of these others or suppress them somehow. So we put additional conditions, more and more conditions. A matrix like this has some eigenvalues. The angle between the principal axis is 90 degrees, and the orientation field is like that. It is a node. But do we get such nodes in mammograms? Maybe. But another matrix, this matrix has angle between principal axis 15 degrees, and this is a node mathematically, but architectural distortion won't look like these. If you take this, another matrix, again, real eigenvalues of the same sign, the angle between the principal axis 90 degrees, look at that. So we don't want these. The condition number of the matrix is defined as the ratio of the principal values. And these numbers are higher than that number. This is about the limit of architectural distortion in terms of shape. So if the condition matrix of the condition number of this matrix A is more than 3, we say don't bother, don't continue with that. So in Fabio's initial work, there were 19 cases of architectural distortion and 41 normal control mammograms from the MAS database. Small database, but that's all the database has. So we put a condition, the matrix A must be symmetric, node and saddle only. Spiral we can throw out. So if the matrix is not symmetric, we don't even process it. If the condition number is more than 3, we don't process it, reject it. So he got sensitivity of 84% at 4.5 false positives per image. Or you could get higher sensitivity if you allow more false positives, but that's not good. But this, at that time, in the year 2003 or so when he did this, this was comparable to the sensitivity of detection and false positive rate for masses. And we were able to detect architectural distortion without masses with comparable sensitivity and false positive. I mentioned a few years before that Naga Modigonda did his PhD on detection of masses. I showed you that, flow field and all that. And his performance measures for the detection of masses was 82% with 2.2 false positives per image. So 2, 4, to double, but same order of magnitude, comparable, but architectural distortion which had been not worked upon earlier as much as for masses. So that was a good result, and he got his PhD for that. And then we said, well, let's make the problem more difficult. The next student came then. Architectural distortion started gaining more attention in the literature in the early 2000s. There were a few papers before that, but not many. And then more and more students got interested in that. But as I said earlier, whatever has been done looks easy. Oh, that's easy, I can understand it. But nobody had done that. So the easy things were done, the next will be more difficult. So we said now, for the next student, we're not going to work with the same database. Take the films before cancer was detected in the mammogram, in the screening program. The radiologist selected cases of what is called screen-detected cancer. A woman has been coming to the program for a number of years. Let's say in the year 2000, cancer was detected. And the radiologist will always go back and look at 2 years before 1998, 2 years before that 96, what was there? Did we miss something? So those previous images are called prior mammograms, prior to detection. And this is screen detected in the sense cancer was detected in the screening program. So we took those, and here is an example. This is where architectural distortion was detected, and this is the mammogram 1 year before. There is something there. But at that time, that was considered to be not significant. Maybe that's why they said come in 1 year instead of 2 years. Or maybe the woman felt something is wrong and came and got another mammogram done. Sometimes the subject or the woman could go somewhere else, or there is something happening, and instead of going to the screening program, she may go to a diagnostic clinic, the hospital, or somewhere else, and then a different procedure is done outside the screening program. Then it is called a case of interval cancer. Between 2 years when the woman is expected to come to the program, she has gone somewhere else and diagnosis is done somewhere else. That information comes to the cancer board, and comes to the screening program, and the radiologist will review the previous mammograms as to what happened, what was happening before cancer was detected. So we got such films. As I said, the screening program is extremely tightly controlled for good reason. I'm not allowed inside, and I cannot even touch the folders containing films or anything. And when these images were digitized in our lab using a high-resolution scanner, laser scanner, mounted on an air suspended table, a member from the screening program came, and one of my students sat with her, and they digitized the film, and in the evening she would take them back. and put them in the screening program. So these are some of those images that were digitized. And as I mentioned, preparing the database itself is a lot of work, months of work. Once that is done, if the database is made public, then others can do better work. They can say, well, you only got 90, I'll make it 95. But there is a lot of work before that can happen. So this is the region and the corresponding region marked by the radiologist. So we asked the radiologist, why was this not detected? And what he said is, well, sometimes some signs are indeed detected. And they may say it is not actionable in the sense it's not clear enough, we cannot take any action, so come back in 1 year instead of 2 years, or come back in 6 months. It could be 6 months, I don't know, 96, 97. So they will ask the person to come back and get additional mammograms taken earlier than the typical screening interval. So one of my students, Shomishta Prajna, she did her master's thesis on analyzing these cases, screen-detected cancer cases, by using the node map as before. In Fabio's work, the aim was only to detect this and just say how many false positives, like those. They were also detected, you simply quote the number of false positives. Next, in Shomishta's work, we said we will detect all of these peaks. And at every peak, we will take a window and analyze those windows by further feature analysis, feature extraction analysis, and classify them. We need a training data set, so train a classifier and then classify. So we will allow 20, 30 false positives at the initial stage. Detect how many hour peaks you have, and cut, I'll show you that. Cut windows, put them through pattern classification, instead of saying, I'll only detect one. So that is what Sharmishta did with the screen-detected cancer cases like these. And interval cancer, I said, is another kind of situation where it is even more difficult in the sense breast cancer was diagnosed outside the screening program in the interval between 2 scheduled screening sessions. So the screening program has old mammograms. But the woman went somewhere else and cancer was diagnosed. That information is not available to us as to the mammogram taken for diagnosis. That is not shared. Only the information that she did develop cancer goes back to the screening program. So the diagnostic mammograms were not available. It is called an interval, just a name here as to what the terminology is. So Dr. Desertel, in the screening program, we went back to the prior mammograms of interval cancer cases, not knowing what the mammogram is on which cancer was detected. And then those images were prepared as a data set for the next student for whom we had to make it more difficult. And this work was done by Shantanu Bonik, who also did the work on the 3D image processing that I showed yesterday. So in Shantanu's work, we had this data set, 106 prior mammograms of 56 individuals diagnosed with breast cancer. These are interval cancer cases. We don't have the mammogram on which cancer was detected, only the previous ones. So the time interval between prior and detection mammograms for 33 cases was an average of 15 months in the range of 1 to 24 months. There were 52 mammographic images of 32 normal individuals, and these were selected to represent the penultimate screening visits at the time of preparation of the database. So what are the normal cases? The person was normal in one screening instant, and we took the one before. So confirmed to be normal in that, and not only at that stage, but also 2 years prior to that. So definitely normal from the screening program. The problem is, these prior mammographic images of women with breast cancer, there is no reference, but Dr. Desertel did a rather difficult task, and regions of interest were marked where he estimated the cancer to have had some signs at that time from the reports from the diagnostic clinic as to where cancer was found. So he had to look at the image, and perhaps the signs were very poor because they were missed by 2 radiologists in the screening program. Or 2 radiologists in the screening program at that time for the interval cancer, these prior mammograms, 2 radiologists had said there is nothing suspicious. And then something happened. How could that happen? Maybe there were some very fuzzy, unclear signs and something developed. Or maybe there were no signs at all and cancer suddenly, quickly developed in a few months. So Dr. Desertel marked these regions and said these are where the cancer was indicated to have developed, and these are the suspicious regions related to what could be architectural distortion. So this database is sort of uncertain, but there is something happening there, is the point. And we said there is architectural distortion, and Dr. Desertel said, yes, there is something there. You can see some fibroglandular tissues going in other directions. Normally, they should all be going like that, and they are going. Here, you see some fibroglandular tissues going in other directions. So those are sites of architectural distortion or suspected architectural distortion in prior mammograms of interval cancer cases. So here is one such example. Now it is all prior mammograms of interval cancer. Gabor magnitude. You can see, once you cut this out and Dr. Desertel says it is there, then we say, oh yeah, I can see it. Especially after Gabor filtering, very clearly there is a scatter of orientation. The orientation field shows that there is a node there in the node map. The full mammogram was processed. I'm just showing a small window of the region marked by the radiologist as suspicious. So then we said, we won't just take that one highest node, we will break the image into as many parts as we can, as the nodes that we can detect. If we can detect 20 nodes, we will take 20 regions. If we detect 30 nodes, we set up to 30. The number 1 node may not always be indicating, the spot indicating architectural distortion, but in this case it is number 1. The highest node is in the region marked by the radiologist. There are a few other nodes. These are the nodes marked up to, I see 26, 27, 29, okay. And 21 is also here, and where is 2? 2 is here, close to the nipple, perhaps 6 is the nipple. So there are a number of others. We don't know what they are, just cut them. And they are overlapping little windows. And we said, take them all and put them through pattern classification. If you don't want 30, take 10. It's up to you. And these regions were marked as true positive if that region overlapped at least 50% with the region marked by the radiologist. The window size is different. These are squares, 128 square or something. The radiologist marked some rectangle. If they overlap, we said all of these are true positives. If they don't overlap, false positive. So look at true positives and look at false positives. False positives are caused by some ducts and ligaments overlapped. And true positives do have this variation in angle. Sometimes not so clear. False positive due to some edge of the breast or something else coming in. Here we can see some other structure intersecting with fibroglandular tissue, maybe a duct or a vessel, fairly thick. So we call these potential sites of architectural distortion. And then did all of these. Phase portrait analysis gives you one value, the node value magnitude. How strong is the node? How many votes were put there at the center of that window? Fractal analysis, fractal dimension. I'll talk about fractal analysis briefly here, and then I have another seminar on fractals. There will be some repetition between these because I prepared these seminars just as 1.5 hour seminars separately, but some things will be common between them. Analysis of angular spread of power. Now, phase portrait analysis is old. Fractal analysis is new, but not our idea. Analysis of angular spread of power, this is where we have, or Shantanu has done a lot of work. Parallax texture measures for comparison and inclusion in case they work. Loss texture, we discussed the filters used for loss, measures of texture energy. So we got a number of features, 80 or so per window, or ROI. And then put them through feature selection, pattern classification, different feature selection and pattern classification methods, different training procedures, classify them as true positive architectural distortion or false positive and throw them away. To derive loss texture features, we applied a transformation, a geometrical transformation. A true positive ROI is shown here, the Gabor magnitude output. You see these fibroglandular tissue patterns at various angles. But the loss texture features are designed to detect what are called ripples and waves. Spots, but we are not interested in spots. Average intensity we don't want. But we wanted to look at the possibility of using loss measures of texture as seen as ripples and waves. But there are no ripples and waves in this pattern. But when you map this by radial or Cartesian to polar transformation, you start seeing ripples. What we expect is from the center of this node, there should be lines at various angles. Sometimes they're not from the center, but at a mathematically exact pattern of speculating radiation will have multiple lines at multiple orientations intersecting at the center. So we expect an angular distribution of those specules. If I do a polar transformation, taking the center of this region, which is the center of a node, as determined by phase portrait analysis, and if I use this as radial distance and then theta, 0 to 160, 360 rather, then these specules will become straight lines. For a given angle, as distance is increased, there is a line that becomes a vertical line. So if there are a number of them, then that looks like a ripple or a wave, but not in the original image. So after geometric transformation of the image and the Gabor magnitude output, we computed the wave detector W phi of loss, ripple detector R phi, L phi intensity doesn't matter, but in Gabor magnitude it shows that pattern. So now you compute the texture energy from these outputs of the loss filters and use them as features, not from the original image. So the geometric transformation is an important step that we introduced. Similar to rubber band stretching transformation of Sahainal and others that I showed earlier, where a ribbon around the mass is transformed to a rectangle. But here this is Cartesian to polar transformation. It is polar, but we are displaying as a rectangle. Sorry about that noise, I don't know what is causing. And then spectral and fractal analysis. We want to get angular distributions of everything. Whatever kind of feature we can detect and relate to architectural distortion, make that a function of angle and get an angular spread. If there are tissues at various angles, then it will be some randomly distributed, maybe uniformly distributed spread of energy versus angle, like a Rose diagram. If there are spicules at all angles, then that will also be spread over multiple angles. But if it is simply normal oriented texture pattern of the breast with all the fibers going in one direction, then the angular distribution will be narrow. So entropy and spread measures can distinguish between those. We can also do this in the frequency domain. So here is a true positive region. Its Fourier spectrum in Cartesian coordinates. In polar coordinates, I showed in texture analysis chapter 7, I showed how to convert this, and now in frequency there is some distribution over theta. So integrate on f for various values of theta, you get the marginal density of s theta. We don't care about variation with f, but in fractal analysis, you integrate over theta and you get the values for different f radial frequency, and that is the radial frequency spectrum. So Cartesian Fourier transform to polar, and from polar the marginals, by integrating along theta and f, you get a function of f, you get a function of theta. If you do only fractal analysis, you do this. If you do only angular distribution, you do this, but there is information in both of them. So this says there is a certain preferred orientation or a few orientations of spicules. And when you take the radial spectrum, radial frequency spectrum, I earlier talked about fractal dimension from Fourier spectra related to fractional Brownian motion in chapter 7. So what you do is plot the radial power spectrum on a log-log plot, log of frequency, log of power spectrum, and it is expected that there will be a portion where it is linear. So to that portion, you fit a straight line, get the slope, and from that you get the fractal dimension. Frequency method. You can do this in 1D and 2D also. If there is no linear portion, then it is not a fractal, or if the slope is almost horizontal. But when there is such a slope, the angle of that, the slope gives, not angle, but the slope gives you a measure related to the fractal dimension. So a few examples. A true positive region of interest and its frequency domain spread of energy or power, now rotated to agree with the angle of the image. I mentioned that there is a 90-degree shift between the angle of the pattern in the image domain versus its energy concentration in the frequency domain. Now if you rotate it, then you may find that agrees with this, and there are some horizontal patterns and so on. It's better representation than this. Simply plotting. If you take the Gabor magnitude again, you get this. There are these spicules at these angles. Take the Gabor orientation and do a similar Rose diagram. Coherence, the strength of the oriented patterns. I described coherence earlier. And orientation strength is another measure that we computed. All of these show a certain distribution. But if you take a false positive region of interest, you only have this narrow distribution of power. Compared to this, it is broad. This is narrow. So using the spread measure, we can reject false positives. Of course, there is some overlap. Not all of them will be like this or the other one. So for each ROI, angular histograms or Rose diagrams computed with 60 bins, minus 90 to 89 degrees, from Gabor magnitude response, orientation angle, coherence, orientation strength, what I showed, based on the orientation field angle at each pixel. The entropy is, as you have seen before, now over angle, f theta log f theta, after normalization. Then we got this result in what is called, shown as what is called a free response receiver operating characteristics. In FROC analysis, you plot the sensitivity of detection of architectural distortion. How many points that you marked are actually true positive regions? I could put multiple points within the region marked by the radiologist. Then you just take one. You rank order them. So if you detect, if the second one detects, then the first one is false positive, and then the others are false positives too. So you plot this against number of false positives. How many marks that you put were false? As I said, I can throw 30 marks as I did initially, And if I detect architectural distortion, I get a sensitivity of 100%. But on all the images, I'm throwing 30 marks. So on the normal images also, I'm throwing 30 marks, 30 points. Then my false positive rate will be very high. So I have to reject false positives and try to increase the sensitivity and pull back the number of false positives. That is, take this curve up towards this corner. It should ideally go straight up, give you 1 sensitivity with 0 false positive. And then that remains. So it should be 2 straight lines like that. That doesn't happen in reality. So if you use only node value, we got this 80% at 10 or 11 false positives, the blue one. By using selected features based on stepwise logistic regression, the Bayesian classifier, and the leave one image out, there are up to 30 ROIs per image, and so many images that I mentioned earlier. But when you train, you are expected to leave the current sample being classified out. But the ROIs belonging to the same image may be related somehow to this ROI that you are classifying. So you say, I'll take away that entire image. All the ROIs of that image should be left out of the training procedure. Or you may say, leave one patient out. All images from that patient should be left out of the training set. Train your classifier and then test with the current case. So there are different leave one out. Leave one what out? So then, by using a neural network, there we got this black line, and using a Bayesian classifier, we got this red line. So now we got 80% at less than 5, or 5.8, somewhere there, 80% and that. Or 90% if you take that, at 8.1 false positives per image. So that was one stage of the work. How many pages I have? Okay, this page, not the whole thing. Okay, this is one stage of the work. And then, okay, we'll come to that later.